Welcome to this lesson on population growth. Today, we will explore two fundamental models that explain how populations increase over time: the exponential growth model and the logistic growth model. Understanding these patterns is essential in ecology as they help us predict how populations of organisms change in different environmental conditions. Population growth refers to the change in the number of individuals in a population over time. This change is influenced by four main factors: births, which add individuals to the population; deaths, which remove individuals; immigration, where individuals move into the population from other areas; and emigration, where individuals leave the population. When births and immigration exceed deaths and emigration, the population grows. Interestingly, population growth often follows predictable mathematical patterns that scientists can study and model. The exponential growth model is described by the equation dn by dt equals r times n. Let's break this down. N represents the population size at any given time. The term dn by dt represents the rate of change of the population, essentially how fast the population is growing. The letter R stands for the per capita growth rate, which is the average contribution of each individual to population growth. This equation tells us that the rate of population growth is directly proportional to the current population size. Exponential growth has several key characteristics. First, when you plot population size against time, you get a J-shaped curve that rises steeply. Second, this model assumes unlimited resources are available, meaning there are no constraints on food, space, or other necessities. Third, under exponential growth, the population doubles at regular intervals, and this doubling happens faster as the population gets larger. However, it's important to note that exponential growth is rare in nature for extended periods because resources are almost always limited in real ecosystems. Here we can visualize the exponential growth curve. Notice the characteristic J-shape. The curve starts relatively flat when the population is small, but as time progresses and the population grows, the curve becomes increasingly steep. This steep rise represents the accelerating growth rate. The population increases slowly at first, then more and more rapidly. This pattern occurs because each generation produces more offspring, and those offspring produce even more offspring, creating a compounding effect similar to compound interest in banking. The logistic growth model is more realistic for natural populations. The equation is dn by dt equals r times n times the quantity k minus n divided by k. This looks similar to the exponential model, but with an important addition. K represents the carrying capacity, which is the maximum population size that the environment can sustainably support. The term in parentheses, k minus n divided by k, is called the limiting factor. When the population n is small compared to k, this term is close to 1, and growth is nearly exponential. But as n approaches k, this term approaches 0, slowing down the growth rate. Logistic growth has distinct characteristics that differ from exponential growth. First, it produces an S-shaped curve, also called a sigmoid curve. Second, the population reaches the carrying capacity and then stabilizes around that level. Third, growth slows down as resources become limited and competition increases among individuals. Finally, logistic growth is much more realistic for natural populations because all ecosystems have finite resources. Most populations in nature follow logistic growth patterns, at least over the long term. The logistic growth curve displays the characteristic S-shape. Initially, when the population is small, growth is slow because there are few individuals reproducing. Then, as the population increases, growth accelerates and the curve becomes steeper, similar to exponential growth. However, as the population approaches the carrying capacity K, represented by the horizontal dashed line, growth rate decreases. Eventually, the population levels off at the carrying capacity. The population may fluctuate slightly above or below K, but it stabilizes around this equilibrium point. Let's compare the two models side by side. Exponential growth assumes unlimited resources, while logistic growth accounts for limited resources. In exponential growth, the growth rate remains constant regardless of population size. In logistic growth, the growth rate varies, decreasing as the population gets larger. Exponential growth produces a J-shaped curve that continues rising indefinitely, whereas logistic growth produces an S-shaped curve that flattens out. Exponential growth has no upper limit, but logistic growth reaches and maintains the carrying capacity K in nature. Logistic growth is far more common. To summarize, population growth follows exponential patterns when resources are unlimited and there are no constraints on population increase. However, logistic growth is much more common in nature because populations eventually approach their carrying capacity. The carrying capacity represents the maximum sustainable population size for a given environment. Understanding both models helps ecologists predict population changes, manage wildlife populations, and understand the dynamics of ecosystems. These concepts are fundamental to conservation biology, resource management, and understanding how organisms interact with their environment.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.